Now, class, welcome to Monday, trigonometry class, the day before the exam. Is that right? I think that's where we're at. So I did want to finish up homework from 3.5 that we didn't. And then if any other questions that you guys have, we can do those. And then we'll jam to maybe like just a quick review session, kind of basic skills review session for chapter 3 if we have time. Real quick here, we left off at 3.5, number 21 last time. I did not explain this very well. And so I just wanted to go through it just to make sure we're all good with it. And then the other ones that we need to finish. Okay, are we good there with that? And then I do have to take roll real quickly here. So, dun, da, da, da. Perfect, Haley. Just on time. That is as good as you can slice it there. That's awesome. Okay, I have Corinna, Hayden, first row. Dun, da, da, da. Amaya, Haley, second row. Georgia, Grace, Nicholas, third row. And going Adrian and Zachariah. Grant is still there. Okay, Grant. I sometimes see your hand. That's about as where the camera is at. So go from there. 10 of you guys. Okay. All right, let's jam with it here. 35. Let me finish up questions, and if you guys have any more or any other further homework questions you guys have, we'll do those as well real quick here. Let's jam. My bad explanation last time here was the lighthouse like this, and we have the beach area. We have it like that. And we have this little D that's over here. It's the distance along the beach that the light shines on from the middle. And so it says that the lighthouse is 100 feet away from the beach area itself. And so what we were talking about last time is how do we get tangent? Tangent is because if you look from this one, this is opposite over adjacent. So the trig function opposite over adjacent would give us this little formula right here. And as you multiply it, you get yourself the formula in terms of D. That's what we want. Okay, but that's just more like the stagnant trig function here. It says that, says from a long straight wall on the beach, the light of the house rotates through one complete revolution every 4 seconds. And that's the other piece of it. 1 second, let me move this to the other screen. That's cool. Okay, so how about this? I think this is the formula we want. And it says that the rotation happens, let's see, it's every 4. So one complete revolution, which it'll go through 2 pi every 4 seconds. So notice that this is now going to be our angular velocity. So it's kind of like you keep this as how fast it's going, right? And then you have this little formula right here. If that's true, then this is true, right? Theta could be replaced with omega t. And so what we do is we replace this little guy, but in terms of t as well. So you're using the formula twice for different things here. This guy would be then theta is equal to 2 over pi over 2t. So 100 tangent pi over 2. T is equal to d. Maybe make it in front here. So there it is. There's your distance the light beam shines from being perpendicular to the beach area. Are we good there? Does that make sense? Does that make better sense than Friday? All right, this says find the equation that gives the distance d in terms of t when d is half a second. So let's do that here. You guys tell me if I'm going too fast. We'll go from there. So half a second. So that t turns into half a second if that's the case. I have tangent of pi over 4. Anybody tangent of pi over 4? I think it's going to be 1, right? Isn't pi over 4 same thing as 45 degrees? That's when you got root 2 over 2, another root 2 over 2. If you want to look at a unit circle, that's fine as well, but I think that's what we have here. So this is 100 feet. So this is lighthouse, beach area, 100 feet here as well as 100 feet here. Okay, then it gets strange. Take a look at this one here. It says what happens to D if tangent or T, T is 3 halves. There's that 3 over 2 for T. All yours to calculate that, see what happens there. I got 3 pi over 4. We good there? Anybody give me tangent of 3 pi over 4?
Negative 100 feet?
I think we'll go with that. Negative 1 is tangent 3 pi over 4. So then we have a negative 100 feet. And that's where things don't add up very nicely. So then the question is, what in the world does that mean? I don't know. Okay, well, I do know. So how about this? How about the lighthouse being right here? The beach area being here? And now we have a light that I think that's shining this way. Let me go kind of like this right here, right? And so the D in our case is on the left side of our perpendicular line to the beach here. So then it's on that side, which is, this is what happens sometimes in mathematics, is the negative sign. We kind of play around with the negative sign. Negative sign kind of gives you direction of things, but then we interpret it in terms of what we want it to mean. So this is 100 feet, still 100 feet along the beach area, is just to the left side of our perpendicular line. Okay, are we good with that one? Last one, and the weirdest one of them all. Let's go. 100 tangent. Let me do better than chicken scratch here. Tangent of 1 second. So it's this times 1. All right, all yours for that one. And this is a good problem here because kind of forces you to think a bit here. especially this modeling mathematics here. All right. Anybody give me tangent of pi over 2?
Is it undefined?
I think so. Let's see, that's when we have pi over 2 is this little corner right here. It's the 90-degree angle. And I think we have 0, 1 here. Tangent of theta then would be 1 over 0. Undefined. All right, undefined times 100. No such thing. It's just undefined. All right, talk to me in terms of our little our lighthouse here. Anybody? What in the world would D be undefined for? Here's the light beam. Like that.
The light beam is parallel to the wall.
I think so. Yeah, let's rotate this little light right here. I'm going to erase it. And so you have the light beams coming straight across like this. There is no value for D anymore, right? Because there's no distance along the beach area that happens to be so. And so at that point, it is undefined. There's no value for it. Okay, are we good with that? All right. Okay, that's 21. Let's just finish up with the others here. This one's an even problem here. 3.5, number 44. And I don't think I gave you guys the answer for 44, huh? So should do this here. We got Mr. Lawnmower on our hands here. I'm going to flip up the lawnmower upside down. Here's my little wheels to my lawnmower. It's a little boxy lawnmower. And I have inside here, I have some blades here happening. So let's see, a gasoline-driven lawnmower has a blade that extends out 1 foot from its center. So I got blades here. Hopefully it's not just one blade on the lawnmower. Usually there are 4 or so, but one of the blades sticks out 1 foot. There it is. The tip of the blade is traveling at the speed of sound. That is so cool, 1,100 feet per second. Through how many revolutions per minute is the blade turning? So all yours here. Quick raise of hands. Raise your hand if you finished this problem already, you know the answer, and it was like, oh, that's easy.
I wouldn't say it was easy, but I finished it.
Finished it. Okay, Karina, good job. And talk to me, guys. Have you guys had chemistry before?
Wait, sorry, can you repeat the question, Mr. Harvey?
Have you guys had chemistry before already?
Yes.
Okay. You guys know when you guys used to do something called dimensional analysis, like changing from one unit to the other units?
Yeah.
Okay. Similar to this as well. This happens here as well. But let's go for it here. So first things first, we got to figure out what we have and what we can put together here. So whenever you have feet per second, whenever you have something like that traveling, then you know you have velocity on your hands because you have a unit over time. And so 1,100 feet per second is pretty cool. And then that blade, that looks like a radius to me. So I have 1 foot radius. Okay, we are finding out how many revolutions per minute. Revolutions per minute. So in these guys, whenever you see that, you're looking for the little omega on your hands. And so it's almost best, especially with these problems in 3.5, is to figure out what variable you have, which variable you want to get to. And then at that point, then you can start figuring out which equation you want for it. And I have to flip through the book here. So I have omega. Oh yes, it's on page 153. And I see something that connects all three of these guys together, which is V equal to radius times omega. And that's probably the best way, at least in my mind, that's the way I kind of do these problems here. See what variables I have, what equation connects them, put them together. Okay, the only thing for here is I'm going to divide by r. And so I'm looking for omega, that is velocity divided by radius. Linear velocity here. You know what? There's no change here, except for the units here. All right, notice the feet go away. And since the feet go away, we are just going to be in, looks like radians per second. That's it. And we want to look at revolutions. Okay, we want to get to revolutions per minute. So here's our fun dimensional analysis from chemistry class. Who and you guys thought you might never see this again here? I think it goes like this, right? Tell me if you guys, there's kind of two different ways to do it here. Is that the way you guys start off doing it in chemistry? And then the question is, how do you get the units the way you want it so that you are going to be in, I think we're in RPMs, so revolutions per minute. That's what I want at the end of it all. So let's deal with the radians here. So radians, I think I have two. Actually, I'll go like this. Radians need to be on the bottom because I want to cancel those. And 2 radians per 1 revolution. I'll take it all the way across. So notice my dimension of revolution is what I want at the end, so I'm good there. Now I got to deal with the seconds here. So seconds got to be canceled, so they have to go on top because they're initially on the bottom. And I want to go to minutes, at least that'll get us there. So 60 seconds in a minute. And notice I can cancel off the seconds units. Perfect, I think we're good. All right, I do need a calculator here. Somebody give me 1100 times 60, then divide it by pi over 2. And we forget all the ones in there. Ones don't matter because you multiply with 1, keep it the same. So 1100 times 60 divided by 2 pi.
I got 10367 and then rounded 3.
Same.
Rounded 3, okay. I go with that here. About 10,000, what, 10,367, and this is going to be revolutions per minute. So that blade, if it's going the speed of sound, it is doing 10,000 revolutions in a single minute.
I said 100, wait,
Yeah, 150.
yeah. So there's a 3 after the 7.
There's a 3 after the 7. There. Okay. Hmm. 60,000 divided by 6. Let me just do that myself real quickly here. 10,000. Brenna, talk to me here. It's 100,000 or roughly 10,000?
Yeah, it's what you put down.
My calculator's up. Let me do this here. Everybody see my calculator? Is that what you guys see?
Not right now, but a second ago.
Uh-huh. Divided by 2 and divided by 3. Should be in the neighborhood of about 10,000 though, right? Is that where we're at? Neighborhood around 10,000?
I got 103,673.
All right, let's talk about it here. So I have 1,100, and I'm going to multiply this out here, times 60. So with that, that gets me 66,000. I'm going to divide by 2, at least this guy here. That should get me to 33,000. And 33,000 divided by pi is roughly going to be what? 3.14 should be about 10,000.
Now I just did it and got 10,504, but I don't know what I did differently.
Okay. Let's see. If anything, it's in class. This is a good one here too. If you use the pi variable or the pi constant to divide by, that's going to give you better results than 3.14. So if you can use pi on the calculator, please use pi. It's going to be.
Yeah, I think that my issue was I didn't put parentheses around the 2 times pi.
Yeah, me too.
Oh, gotcha. Okay, there it is. Okay, now we're good. So you're multiplying by pi instead of dividing by pi. Okay. Sweet. Okay. Tell me real quick here. Tell me the answer here. 10,000.
504.
504. Okay. Revolutions per minute. That is neat. Real quick here, got to share it with you guys here. So in the military, because I was watching a documentary here, they were talking about super choppers. So first of all, super choppers, their blades, they're just the new advancement in helicopters, in the military. So instead of having a metal blade, what they have or they're developing is it's almost like a cardboard kind of feel for it. And, so I don't know if you guys want to, I think it's called Super Copter. I think that's the Super Chopper. I think that's the documentary here. But it's 2 things that are happening here. First of all, they made it lighter, and the blades are not metal. It's a different mesh. So if a bullet were to go through it, in metal, what happens is it starts to disintegrate and starts to crack. With this sort of almost like hard plastic, you get a bullet that goes through it, it punctures it, but it doesn't affect the blade at all. Blade is still functional just fine. And so what they also did is they extended this. They extended the blades out a little bit further. So the rotation is still happening the same, right? But by extending the blade further out, now you're going the speed of sound. And because you're going the speed of sound, you don't have that little whirling sound anymore, like a helicopter sound. So pretty much they made it almost like stealthy just by extending it. I think it was like 2 feet more. They extended less than 2 feet more. But because of that, it dropped that little, you guys hear a helicopter all the time, right? It goes this little boom, 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 boom sound. Well, by hitting it so it's this, when the chopper hits the speed of sound on the blades, the sound disappears. And so it's totally silent. That is like interesting. Anyways, something had to do with a lawnmower blade, which I thought connected pretty well. Okay, are we good? Next one. 45, I think, is what we got here. 45. We got a cable car in San Francisco. San Francisco cable cars travel by clamping onto the street cable that circulates the channel underneath the streets. That's cool. And they get electricity from above. The cable car is driven by a large 14-foot diameter pulley. All right. Here's my little pulley. It is 14 feet above, and PowerPoint's still trying to catch up with the math here. There it is. Okay. Called a sheave. The sheave turns at a rate of 19 revolutions per minute. Slow guy compared to what was on the lawnmower. But I guess we don't want people traveling in a cable car throughout San Francisco going 10,000 miles per hour or 10,000 revolutions per minute. That would not be good. So find the speed of the cable car in miles per hour by determining the linear velocity of the, okay, they gave it to us. That's kind of cool. So what do we have? I guess we have diameter here. Diameter is equal to 14. And we got this revolution per minute. Okay. So then what we have to do from there, let's see. We need to get to V again, right? Let's see, what do we know? I guess that we can convert this into R, right? R would be 7 feet. Everybody agreed there? I think we're probably going to use the same formula. Okay, so this guy, kind of careful because students get mixed up all the time. That guy would not be omega. That's just revolutions per minute. You need to tack on that little 2 pi next to it. That will get you omega out of this. And so if that's the revolution per minute, if I take that 19 times 2 pi, gets me what, a 38 pi? Now I'm at radians per minute. And now I could say this guy is omega. Okay, cool. So I got R, I got W, and then the question is what connects those two together? Because I need V at the end of it all. And it's the same exact formula again. There's my formula right there. All right, so let's go with it here. So let's see, this would be 7 times 38 pi. Anybody give me that? And I'm going to get the unit values out of this here. This would be feet. The radians go away because they're just a real number. Feet per minute. I think that's what we're at. All right, 7 times 38. Anybody? And we can keep the pi just kind of separate. Don't multiply the pi in, but just the 7 times 38 to give us an exact value.
I got 266
Say again.
times 38.
2 something something. 256. I think that's what I heard. Is that right? 256?
66.
66. Feet per minute. Awesome. Okay. And I think we're ready. Here's our dimensional analysis again. 266 pi. I got feet. And we're going to go like this again. And minute is down here. So all yours to try this one now. I need eventually in terms of miles on top per hour. That's what I need. So how fast are these cable cars moving? All right, try yourself first here, since we did it last time here. So converting each of the units to what you want them to be. So it looks like I need to go feet. I need to get to miles on top. So I am going to cancel off the feet on the bottom and put miles on top. Anybody how many feet in a mile?
That's not right. Is it 5,280?
I go with that. Perfect. Good job. Okay, feet are gone. Okay, now we go minutes to hours. So minutes have to go on top over here. Hour on the bottom, so that the minutes will cancel each other out. And that's perfect. That's what I want. Notice now I'm in terms of miles per hour. All right, so let's go with it. 266 now times pi. And then whatever you get for that divided by 5,280. Oh, sorry. Thank you so much. Thank you. Almost forgot the 60 there.
Wait, aren't they, shouldn't hours be on top?
No, because you have to cancel out minutes, so you have to put it on minutes. You have to
Oh, yeah. Never mind.
Oh, no problem. Okay, now how about 266 times pi times 60 divided by 5,280? What do we get? All right, should I do it on my calculator as well here? All right, I'm gonna, let's see if I
9.5 rounded.
round it. I'm gonna go with that. Yeah, that sounds about right for a cable car on the San Francisco streets. About 10 miles an hour. 9.5 miles per hour should be about it. Okay, these guys are a little bit tough here. So glad we're doing it together. We're good. Hopefully making sense. Is it making sense? Maybe.
Yeah.
Okay, we got one more to do, a ski lift scenario here. Uh, 3.5, number 49, I think. We got the last one here. Ski lift operates driven by a wire rope. And on the next page, there's like a little bit of a picture for it here. There's a, I'm gonna do this little drawing here. So boom, goes like this. Here's the rope coming in, and the rope goes out like this, and pulls all the skiers. All right, if the bull wheel is 12 feet across and turns at a rate of 9 revolutions, here it is, per minute. Notice it's the same exact setup as 45. Let's see if we want the same thing here. Yep, linear velocity in terms of feet per second, someone riding on the lift. And so we want Stickman to see how fast Stickman is going if he's sitting on one of those seats or being dragged, depending what slope you're on. Okay, guys, real quick here, very, very similar to the last one here. So see if you guys can go ahead of me on this. Exact same setup is given. Give you guys what, 30-second head start, go for it. This is 9 revolutions per minute. I think you want in terms of omega here. You just want the radius out of here. So I think you want those two pieces. And then we got ourselves this little formula that will happen. All right. I'm gonna go with 30 seconds are up. So how about 6 feet for the radius, and how about 9 times 2 pi or 18 pi? We'll go with radians per, what is that, minute, I believe, right? Radians per minute, there it is. That's what I got there. All right, let's see. 6 times 18 pi, I think that's what we're looking for.
It's 108.
Perfect, thank you. And looks like we are in feet times radians divided by minutes, and then radians go away because again they're just a real number here. So it looks like I'm in terms of feet per minute. It says one. Yep, that stuff again. Look at that. All right, hopefully that was good. Just because we did 3 problems that were very similar here. So we want it in terms of feet per second. That's what I want here. Not much to change. Feet is already on top there. I already got what I want as far as feet is concerned. So minutes just need to change into seconds. That's about it. So minutes on top, seconds on the bottom to cancel those guys out. And then it would be 60 seconds on the bottom to a single minute on top. I think we're good there. And all yours, what do you guys get?
I got 5.65.
I'll go with that, yep. 5.65 feet per second is how fast we're traveling there. Boom, okay, cool, homework is done. Let's see. So when you come, we'll do some review problems in just a second here, but just to mention here. So on Wednesday, I think we're almost all ready for the exam, is that right? You guys will come in. There are 10 questions that are going to be non-calculator. Then you have 10 questions that are calculator based. All right, then you're gonna have 3 honor questions. So it's going to test not only your knowledge of it, but a little bit of how fast you guys can do it as well. Are we good? There's a little bit of a time component here. So once you finish with the non-calculator, jump to the calculator. Should be about halfway done in class when you jump from the calculator to non-calculator. And then you have 3 honor questions that come along with it as well at the end. All right, are we good?
Wait,
Grace has a question.
Yeah.
if we finish it during the class period, will we have more time to finish it? Because I know personally, I can't work that fast.
Okay, let's see. True. I do want to do it in a single class period. So if anything, I might just reduce the questions a little bit more than, so that's true. That may be a little bit too much. Let me see. Maybe I could reduce it down to about maybe 18 or 16 questions each, just so you guys have the time. But I do want it to be part of a, not to linger on the questions themselves, right? Part of it is just to say, okay, yep, I do know this. Let me let me do it this way. Some are going to be really easy, like find the reference angle. Those should be pretty easy just to do, put together and stuff. All right.
And then is the homework is still due tonight, and then the challenge problems are also due tonight?
All perfect. Thank you so much for asking. Since the test has been moved, I'm going to have the homework due Wednesday night and the challenge questions due Wednesday night. Are we good? Those, if you could turn in online, and I'll have a separate place. I do have the place for the homework already set there. I just need to put in the challenge questions. I think I'm just going to call it project for chapter 3. That's probably going to be the way it's labeled on your Google Classroom. Okay, are we good there? I mean, good question there.
Yeah, thank you.
Uh-huh. Yeah, I just wanted to make sure you guys are all good to go. Test itself. Okay, even if I don't change the due dates on the homework due, just know it's due Wednesday anyways. I'm not going to cut off. I'm not going to put a late penalty for the homework. Okay, are we good there? So any other questions on as far as test is concerned? Okay, I'm going to set up this little guy right here just as a quick review, just before the test, more like a skills kind of test. Actually, I should say, any other homework questions that you guys did during the weekend, and then you say, what? I need help on that one. Totally forgot about that. No? Okay, we got, let's see, 10 minutes here. Let's see if we can go through some of these really quick here just to get more of a familiarity with it. Can I pick on you people here? I'm going to just pick on just however it goes. I'm going to go from the left side of the class to the right side of the class. So Corinna, you got first one. Hayden, you got B. Amay, you got C. And we'll kind of go through, I think we'll probably go through the rest of the class here. You got the easy ones though. All right, just tell me when you're done. Tell me when you're ready. Or to give me the answer, any one of those. It's okay. All right, should be fairly easy. These should take you about 4 seconds each. And go. Whoever wants to go first.
A is 30, I think.
Absolutely. 30 degrees, you're already in quadrant 1. And because you're in quadrant 1, the reference angle and the regular angle is exactly the same. Good. Ding, ding. Next one.
B is 60.
60 degrees. 240. You're in quadrant 3. You are 60 degrees more than 180 degrees. 60 degrees would be the reference angle. Perfect. Next one.
I might be wrong, but is it 30 degrees?
Let's see. Oh, PowerPoint catching up with mathematics here. And I believe you are right. So if you go 110 degrees this way, right, because you're going the negative angle, you will be in quadrant 2. And at this point, you are still just an extra 30 degrees beyond the 180 or the negative 180. So reference angle, 30 degrees. Is everybody okay with those? Going once, going twice. Cool. Pick on some more people. Here we go. Tell me if I'm going too fast as well. We'll go from there. Find the exact value. Haley, you got A. Georgia, you have B. And this is exact values. Maybe the calculator might not help you here on this one. We'll see. Okay, boom. right, does some funny stuff here. There. All right. Tangent 315 degrees. Anybody or Haley?
I totally forgot how to do this.
No problem. No problem. So 315 degrees would be about right over here. And so if you go around, this would be 90, this would be 187, 270. And so here's your 315. And so what we are interested in is just this little piece right here called the reference angle. So how far away is 315 from 360?
45 degrees.
Yeah, 45 degrees. Okay, if that's the case, then you got yourself really just a 45 degree, 90 degree triangle. This means this is negative. Oh, sorry, positive. Yeah, positive root 2 over 2. This is a negative root 2 over 2. And tangent would be the y value divided by the x value, or -1. Okay, Haley, are we good with that?
Yeah, sorry, I totally forgot how to do that.
No problem, no problem. That's why we're doing it. That's cool. Okay, Georgia, up for B.
Yeah, I got to, so it would be just small angle, right?
Uh-huh. So 300. Oh, let's see, is a small angle, a big angle? Let's see, we're 60 away from, that should be 300, right, Georgia? Which quadrant are we in?
Oh, part of it.
Quadrant 4, or like this. And we got ourselves an extra 60 degrees to get to 360. If that's the case, that means the coordinates here are going to be, this is the small side, that's the large side right here. So small side has to be a 1/2. The large side has to be the root 3 over 2. And now we have fun because cosecant is 1 over sine of 300 degrees. And sine is root 3 over 2. Cool, good there. And it's just going to be the reciprocal of it. So you can keep it like this. This is totally fine like that. Let me erase the previous. Or you can rationalize the denominator and make it 2 root 3 over 3. Either one is just fine right there or right there. Okay, you all good to go there with that one?
Wait, so is it negative?
Thank you so much. Perfect. Negative there, negative there, negative. Thank you, Karina. Good eye on that one. Okay. A minute to go. Grace, of course we're going to have to get to you here. So cosine of 495 degrees. Oh, and then I almost forgot here. Can I have someone spray down and wipe down the desks that are being used? Don't need to do the ones that are not used. So 1, 2, 3, 4, 5, 6, 7, 8, 9, just the 10 desks that are used.
Yeah, I can.
Awesome. Thank you so much. So Grace, it is more than 360 degrees. So you have to figure out how much more.
So it'll be in quadrant
102, perfect, okay. So we're gonna go, technically go all the way around like this, right? Here's 360, and then we're going this way. And then you almost want to mention how much further than 360 degrees. So you can actually just subtract this out. Oh yes, that's cool. It's 135 degrees more.
So that'd be 45.
Perfect, 45-degree reference angle here. Awesome. I know that to be a negative root 2 over 2, positive root 2 over 2. And the answer is
Wait, I can't remember what's your next.
oh, no problem, no problem. Cosine is going to be the x coordinate, right? As opposed to sine being the y coordinate. And if that's the case, we're just going to take this little guy right here. Boom, answer is negative root 2 over 2, and we're done. What? So it looks like we got through not all of them, not everybody here. Okay, 825. I should quit here at this point here. So let me do that. I'm gonna make the test a little bit smaller for you guys to, shorter for you guys to get through. And then the other thing, let's see, can I bug you as well here? Up in front of the classroom, there is the cubicles, and inside of the cubicles, there's a box of formula sheets. Can you just make sure there are 1, 2, 3, 4, 5, 6, 7, 10 of those there for Wednesday? If not, then Miss Rainey will have to copy some more.
Are they these ones?
Yeah, Are there at least 10 there?
I got the stickers to work last week.
Yeah, there's at least 10.
Okay, perfect. Awesome. Okay, that would work. Thank you so much. All right, y'all have a good day. See you guys later.
Thank you.
And yeah, I think it was May that said it can spray down the desks there.